looking at some people here, and I think that's a great opportunity for our friend Jevon to volunteer. All
right. Our next speaker is Greg Fuchs, and he's going to talk about quantum and nonlinear magnonics.
Great, thanks. So thank you guys, and thank you, Carlos, for doing all of this. This has been really fun. All right, so why don't we just jump into it? So here's what I wanted to talk about, hence the name quantum and nonlinear. So this first one, as we've heard, is actually not quantum. It's a cavity magnonics experiment that is explained by pendula, so we don't need to call that quantum. But we're interested in pushing it in that direction. And so then the second part, we will do that in theory. So this is a little bit of a scary moment for me, because those of you that know me know that I'm an experimentalist. And I normally don't publish theory papers. But we had this idea and we thought, oh gosh, this is deadly simple. Maybe we should maybe we should write it up. And so we did that. And I'll tell you about our thoughts there. And then this is unpublished. We were just about to post this on the archive, but it should be a lot of fun, and it follows a little bit about what Dennis was saying earlier. So, okay. All right, so I want to give a broad introduction. I've been interested for a long time on hybrid quantum systems of many different stripes. And we've heard about several of them today. We heard about spins and magnons. We heard about photons and magnons. But if you think about the simplest possible, hybrid quantum system that you have at least these two elements. You have a qubit. If it's just two linear oscillators, it doesn't have to be quantum, as we've already heard. That was already discussed this morning by Jorg. But if we have a qubit, actually, it is quantum. And then some coupling, and then some kind of harmonic oscillator. And I would view this as kind of the Lego blocks of modern quantum technologies. And certainly this is a picture of the unit cell of superconducting circuits, but many quantum technologies are based on this concept. So from the qubit, we get an intrinsic nonlinearity. It's generally the thing that we use for logic, although it doesn't have to be. And you can imagine many different types of qubits, and three are here. The resonator could have many different uses. It could be used just for reading out the qubit. It could be used as an interconnect. It could be a very long-lived memory. People can make really outstandingly long-lived bosonic modes. And it could have a nature that's based on many different things that are basically bosonic. So it could be either microwave or optical photons. It could be an acoustic mode. It could be a magnon, which is kind of our purpose here. Now, as we get more and more hybrid, we could add more elements. So we heard this morning from Dennis that you could, for instance, make a coupling to a color center, like an NV center. And then you have the interesting opportunity to then have that information fly out into the world in terms of a photon. So just a kind of broad vision of where we might want to plug things together to do things. All right. Now, oftentimes, as we try to understand and get handles on a system, it's best to start out either with a classical system or a simple system, and then push it more and more into the nonlinear regime. So that's kind of, one way of viewing cavity magnonics is we have a linear coupling between a microwave resonator, in the case of the experiments that I'm going to describe, and a low damping magnet. And these are both harmonic oscillators at their core. So this is just, a couple linear oscillator system. Nonetheless, it's very rich. So if your papers aren't on here, I apologize, because this group has got a very impressive list of different things that they've published on. But there's lots of interesting stuff that you can do with cavity magnonics. So for instance, you can read these reviews, and they really do say a lot of things about what can be done. They can be used for sensing, especially via the dissipative coupling. You can introduce non-reciprocal effects. You can introduce non-Hermitian effects, and they have some very interesting properties there as well, exceptional point physics and other things like that. So the cavity magnonic system, even though you may start by saying, okay, it's two coupled oscillators, maybe not much new there, actually I think that it is a very interesting and rich space for doing research. All right, so I want to start with the linear cavity magnon coupling. We've already heard this today, so I'm just writing down the kind of simple Hamiltonian here, where we just write down the resonator energy. I'm going to just, for now, focus on the kind of Cattell mode or K equals 0 magnon mode. Other stuff will come up later. We've already seen that this morning. And then their mutual coupling. And this is the most common form of that coupling that you see in the literature. This is the so-called XX coupling, because what we have is really just like the X operator for the magnons times the X operator for the photon cavity, and then we disregard the terms that are not energy conserving. Okay, so this is really considering the on-resonance case. There are other cases that one can do, but this is the simplest one. And the way to understand this kind of coupling is it's saying, in the classical domain, that a displacement of the resonator will cause a displacement of the magnons, and then vice versa. So if I want to write it in terms of raising and lowering operators, it's not necessary to do that, but if I do it, I can view it in terms of I can create a phonon in the cavity by annihilating a magnon, or I can do the reciprocal operation. I can create a magnon by annihilating a photon. And this is very well known. So we've already heard an extensive discussion about strong coupling this morning, so I will be very brief here. But the usual thing is that, and by the way, I have a 4 here. We didn't see the 4 this morning. Some people use the 4, some people don't use the 4. The 4 depends on your definition of these line widths. So please don't get upset about the 4. Okay. But the basic idea here is that if the coupling rate exceeds the damping rate for both the resonator and the magnons, then the quanta are being swapped back and forth. And so now you have a totally hybridized system that has an excitation that's joint magnon and photon. And one of the ways that people parameterize that is via the cooperativity. You still have to meet this condition. So you still need to have the coupling greater than both the damping rates. But it's often useful to give it in terms of a cooperativity, which is just the ratio. We heard that from Dennis this morning. And then, you want that ratio to exceed 1. And one way of thinking about this is simply, as we already saw, you get this avoided crossing. Now, if these things are too large, what happens is the line widths are going to sort of fill in this gap here. And then if I take a cut, I actually won't see 2 separate resonances that are split apart, and I'll just see sort of one smushed together thing. All right, and I just want to reemphasize, so this is a nice review paper from Kan-Ming Hu's group, and they, for instance, describe this system exactly as 2 coupled pendula. So that physics is totally correct, junior level, intermediate mechanics. Okay, so I think everybody has already been aware of all of the nice work in the field, and I'm not going to do all of it. I just want to make a few highlights. Yig spheres are kind of the sort of most dominant force in cavity magnonics for the last several years because of their nice properties. So they kind of have the narrowest low temperature line width of a megahertz or even below. They don't, because they're big, you need a big cavity to put it in. So you don't get a very good filling factor. So the actual coupling per photon is low, but there's a lot of spins in a 1 millimeter Yig sphere. So you actually get quite strong coupling. And so, for instance, these papers in 2014, one from Nakamura, one from Hong Tang, easily show things like cooperativities in the 3,000 range. So that's great. My take on this is an awesome way to do physics. But if we ever want to like penetrate the technology in the quantum space with magnons, probably this is not the way to do it. It's going to be, well, if we want to make circulators, maybe it's fine. But if you want to make a small circulator, it's not fine. And you want to make a small circulator, in my opinion. So I think the big issue is that it's big. It's limited in terms of the way that you can couple these together and the way that you can scale. But it has really been a trailblazer in terms of, like, for instance, the first experiment coupling to a trans-1 qubit, things like this. So thin films make sense. I want to give a nod to Hans's beautiful work, which is, I want to point out the first experimental paper on cavity magnonics. And so they flip chipped a resonator like this one with YIG and saw some really nice results, high cooperativity. Line width, though, unfortunately doesn't match what you can get with the YIG spheres. And I think that's a serious issue and one that we should keep thinking about. And so people have done this in different ways, and I'm not giving all the references that exist, but this is still with YIG. And then we also heard about this work earlier, where you can try to think about kind of more integrated platforms. And the first attempts at that were using permalloy. And you can, permalloy is very dense with spins. Density is high, so you can get good coupling rates, but the line widths are much worse because it's a conducting magnet, and just full stop, that's a problem. There's this nice work actually from NIST where they use the cobalt iron 7525, and actually it's surprisingly good. Okay, but the bottom line is that sort of transition metals are maybe not going to get us into the quantum regime that we want to get in. All right, so the Magnon line width is important, and I just want to point out that, like, probably there are people in this room that know more about this than me, so a little bit of caution on this, and this will be the topic of the discussion that I want to say tomorrow. So I just have one slide. This is the way that I think about the line width, where I have the Gilbert damping, which is just literally just means it's the viscous term. It has a frequency dependent, that's it, nothing, no other definition. Then there's Magnon scattering, there's inhomogeneity. So for instance, if I have a variation in the anisotropy of my material, then different parts of the sample come into resonance. And then, as we heard earlier, you get sort of actually a multi-mode kind of a response, which is bad. And then TLS, which has been studied, and I'm not talking about it right now. But for those of you that were wondering about the Magnon scattering, you actually don't need high powers and nonlinearity to get Magnon scattering. Just defects are enough. So if I just have a magnetic defect, it provides the kind of spatial frequency that I need to convert a k equals 0 magnon into a high k magnon, and that looks like damping because it's leaving the mode that I'm interested in. Okay. All right. The main focus here in this first part of my talk is, yeah, go ahead.
Does it have to be an elastic scattering?
That's a great question. So I am not an expert in Magnon scattering, so there's probably people that are experts. But from what I understand, the spatial frequency just gives you the kind of mode matching. It's just like in optics where I have a light line and it just gives me, like, if I want to scatter a photon into a different mode, then I need to provide that momentum. So I think the short answer is it can be elastic. Does that mean that there's not inelastic? I don't know about that.
You can have there an entire hierarchy of scattering elements, including elastic and inelastic scattering. And so my naive picture for the elastic one is that you might naively lose it because you are going to a different place in k-space, and then you are not connecting it to your microwave any longer because you're restricted in the coverage of your k-space that you can address with your microwave lines.
There you go.
And it's lost.
Yeah. All right. Okay, so the material that I'm going to talk about, I understand that Zeke talked about it in great detail yesterday, and so I'm going to maybe smooth over this a little bit, and he's also going to talk again on the materials. But you know, we had a kind of really interesting discussion now back several years, and this is a quite long-standing collaboration that we've had along with Michael Flatte. Oh, I just got my step goal, everyone. Isn't that cool? Okay. And it's this material vanadium tetracyanoethylene, which is, I think of as kind of like organic YIG. It's not YIG. So YIG is the kind of material that everybody goes to for cavity magnonics because of its low damping. VTC&E is in a very different regime, actually. So, you know, it has a very low magnetic moment. So the density of spins is small. It has super exchange between the vanadium atoms and the TC&E ligands. And, you know, it's actually surprisingly high Curie temperature. But of course, what is most interesting about it is that it has very, very narrow FMR line width, and at room temperature, the Gilbert damping parameter can be kind of in this range. And this is an honest range. Like, this is the range of samples that have been shipped to us from Zeke's lab. So sometimes the growths are amazing, sometimes they're not as amazing, but the point is that it's a very low damping material. I guess I'll skip over this, but one of the cool things that also drew me to this is that if we want to make very complicated like structures integrating with qubits and so on, you know, the aluminum oxide tunnel junctions in qubits hate any kind of annealing. So you really love the fact that this kind of low temperature growth, you can just put it on after the whole chip is fabricated. Yes, you can.
I'm just not agreeing with your statement about the annealing of the tunnel junctions in
aluminum oxide tunnel junctions are famously drifty. If you anneal aluminum oxide tunnel junction, its Josephson energy will change dramatically and all sorts of things.
It's not so bad.
Okay. Well,
I have a good experience.
Okay, well, then we should talk. I'd be interested. But what I see in the literature is like 10, 20% changes. And it depends on the temperature of the anneal. So if you want to grow YIG, you're at 600 degrees C. I think the aluminum evaporates. So, yeah.
I was thinking more about 300 Celsius or so.
Yeah, okay. Fair enough. Anyway, all right. And then the third ingredient is that you can pattern it very beautifully. You can pattern it by liftoff. And this is some magic that Zeke's group developed using solvent chemistries that allow you to remove the PMMA template without dissolving the VTC&E itself. And most critically, this kind of liftoff processing doesn't actually change the damping parameter if you're careful about the way that you do it. So they're able to show that a continuous film and say these 25 micron disks, actually the data just lie right on top of each other, and they have the same very low damping. So that's really cool because that means that we can now design structures where we integrate, you know, some superconducting circuit with VTC&E that we pattern in a microstructure, and we hope to get the same kind of narrow line widths. All right, so let me talk about that experiment. So I won't go and talk about all the like modeling of the resonator because I think you've all heard this. This is a lumped element resonator, as it was already a type already discussed this morning. So you just have an interdigitated capacitor and then a short, which is the primary inductive element. And what we do is we pattern the VTC&E all the way along that. So it's 6 microns wide and 600 microns long. We need it to be big because VTC&E has a low moment. It's also encapsulated. In this experiment, it was encapsulated with epoxy and a cover slip, which is the same kind of like technology that your smartwatch and your cell phone has for the OLED display. So that's actually where the epoxy is coming from. And you can see the kind of epoxy front right here because this is where the good VTC is, this dark color. And then over here, these are the like E-beam markers where the exposure was done, and they're not covered by the epoxy, so they turn color, and that's how you know it's denatured. Okay. So here's the resonator characterization. This is a zero field measurement. We just take this thing, we stick it in our helium-3 cryostat, we attach it to VNA, and we measure the loaded quality factor, which here is a measly 4,000. So the frequency is 3.6 gigahertz, and so this gives us a damping rate of a bit under a megahertz. By the way, these are the worst devices we've ever made. This was the very first chip that we ever made. The whole thing worked. So that was amazing. We now can do 10 to the 5 Q for exactly the same patterning. So the way that you do the fabrication matters a lot. And I just want to highlight, this is work with my collaborator Vala Fatemi, who's a superconducting circuits and materials guy. And we just recently demonstrated that two kind of amazing things. One is that you can do acid-free processing of regular lambda over 4 resonators, get low power quality factors above 10 to the 6 with only 3 micron gaps. This is using the Boulder mask. So that's these points here. Okay, this is no HF dip. Some of it is with a dip, some is not a dip. And then the other thing is that the niobium was grown in a spintronics chamber that has been sputtering magnetic materials for the past 20 years. This was a chamber that came to Cornell when I was a grad student, and I took care of it. And just by some careful hygiene, we have been able to grow niobium that is apparently state-of-the-art. So it's kind of a little bit against the intuition of what people had, like keep my magnets away from my superconductors. Turns out that's not necessary. In fact, this point was sputtered with magnets and superconductors in the same, co-loaded in the chamber with like interleaved growths. So you can do it, yeah. Room temperature.
The question was, what was the substrate temperature for the recording?
Silicon. Okay, anyway, so I'm not the primary mover on this work. I worked on it with Vala, we collaborated, but the message here is that processing matters and hygiene matters, but you can get really low loss superconducting resonators with niobium by taking simple steps. Okay, but back to our main story here. So we've already seen the avoided crossing. So here's another one. So here you have essentially, where the resonator would be without the magnons, where the magnons would be without the resonator. But of course, you get this nice avoided level crossing. What was interesting too, and we saw something similar this morning, is that in addition to the main gap here, you have these like little streaky guys. If you kind of have to dial in, change the saturation on your plot, and you get these streaks that follow kind of the slope of the magnons. In fact, if you look carefully, they have little crossings with the main mode. And we saw this and we're like, what the heck is that? Okay, so at first we were very confused. People have reported this before, but one of the issues is that YIG is in a very different regime than VTC&E is. So I'll come back to this because it's an interesting story. But let's first just analyze the uniform mode resonance. So you've all seen this math before. We heard it earlier, so let me just give you the main outputs. So we know that the resonator line width gives you about a megahertz. You can get the coupling by just the distance between these modes. And so that's this 90 megahertz. You can also figure out what the magnon damping rate is, and that is 30 megahertz. So that gives us a cooperativity of a little over 1,000. So this is nice. But to be honest, we were a little disappointed by this number 30 megahertz. So this is sort of like good, or maybe even at the time the best for a thin film kind of a sample, but it only marginally better than what people have done, and nowhere near a YIG sphere, okay? So that's an important thing. But we learned something really interesting about the materials by looking at those little modes. So let me tell you about that, because I think this is an important point. So these little streaks that I'm pointing out here are just the thickness quantized Magnon modes. You can open up Catel's book and find them in there. And so, yeah, they couple weakly to the resonator because they have a total effective dipole that's smaller by the mode index. And so they get weaker and weaker coupled as you go to higher and higher order, but we see many, many, many orders. All right. Now, what's pretty obvious just from looking at this picture is that their line width is much narrower than the uniform mode, much, much narrower. So why is that? What's going on? What can we learn about it? First, let's do some detailed analysis. So you can just do the basic input-output theory that people have published on before and just basically adjust the parameters until this picture and this picture look the same, okay? And so that includes like matching these line widths from the model and as well as their positions. And then when we get all those parameters, we can just make a table of all the parameters. So here's the Magnon mode number. Here is the index coupling rate. Here's the mode indexed frequency and the mode indexed damping rate. So I want to remind you again that the uniform mode coupling rate is 30 megahertz. Damping rate is 30 megahertz. And what you see is that and the coupling rate is 90 megahertz for the uniform mode. But then when you look at the higher order Magnons, the coupling rate goes down as a function, as the mode index goes up. That actually makes sense for the reason that I just gave. The total dipole gets smaller. And, but also the line width gets narrower. Yeah.
So in principle, if your picture is correct, then you would be able to estimate GN from the standing wave argument that you gave. Is that fitting there? This decrease in G?
It's not a fit. It's a by hand parameterization because there's so many parameters that if you do a global fit of the S21 data, it just doesn't work.
What I mean is if you take the higher order modes,
yeah,
and you think about basically the amplitude area that gives you the rough estimate how good this couples to.
Oh, that works. Yeah.
Okay. Thanks.
Yeah, that works. Okay, so the key point here, the key materials lesson, was that thin film YIG, thin film VTC&E has much worse line width than YIG spheres. Question is why? Okay, and is it a materials issue? Like just thin films are worse than spheres? Is it a shape issue? What is the issue? And one of the things that we can say here pretty definitively is that it's not a materials issue in VTC&E, at least, because we're getting the same line width as a YIG sphere here at 400 millikelvin. And so, compared to YIG spheres at dilution refrigerator temperatures, actually. So the material damping quality internally is excellent. And the loss rate of the uniform mode that's higher is something that we have to understand better. My thinking is that we could be better microwave engineers, for instance, that maybe the uniform mode, which has this big dipole, is coupling to other lossy modes, and that's maybe what the issue is. That's my intuition, but it's hard to prove unless you really get it to go to 1 or whatever this material's limited value. But from a material standpoint, this looks really, really good. Oh yeah, animated it, okay. Got it. All right, so that's where I want to end on this first story, that we demonstrated that you could do strong coupling with a very alternate material than the YIG that most people are working with. This vanadium tetracyanylethylene, you can get really good cooperativities in these materials. The Magnons don't seem to be limited by the bulk material damping, for instance. And it's just a really flexible platform. So, you can lithographically pattern it, you can think up any structure you want, you can write it in CAD, and then you can make it. So that's a very attractive and exciting aspect for me. All right. So now I want to move on to what we think is, oh yeah.
Sorry, just when you're talking about as a materials point of view, it not being, being great but not being better than YIG for some reason, wouldn't that reason just be the magnetization that is substantially lower? Because I think when Sylvia was talking about this earlier, the coupling is directly related to the magnetization.
No, but
Right.
we just have a bigger volume, so the coupling is the same. The coupling has nothing to do with the damping. I'm focused on the damping.
Right, okay. So
And-
your coupling will be the same because of the volume.
Because of root N, yeah.
Right, okay, thank you. Sorry, I think
So you didn't actually write the master equation that was used for the input-output theory, but I just want to make sure I understand the definition of the damping rates that you have there, because the rate of loss of magnetization is proportional to the occupation of the
Yeah.
of the mode. So the occupation number is taken out somehow, or not, because these numbers that you have, are they the are they the rate of energy loss, or are they the rate of magnon loss? Do you know? What I mean?
They are the rate of, the rate of magnon loss. They're the. This is an
I'll just
excellent
say
question,
the
and I'm
prob-
being very cagey because now we talked about this and we discussed it and we included it, but now I want to be very careful that I give you the correct answer.
Because I could interpret the change in these numbers as you go to higher mode index as just suggesting that the higher modes are less occupied than the lower energy modes for some reason.
Right. There is no power-dependent line width changes in the
Okay.
regime that we're in.
Okay.
Um,
That suggests
we're-
the numbers are independent.
Yeah,
of
we're
the-
measuring at like minus 100 dBm or something like that, which is not single photon, okay? That's like minus 140.
Yeah.
But we're very far from every nonlinearity that you could have.
Okay. Okay, thank you.
Regarding the damping and how you extract it, so I assume that you do this in a decently off-resonance spot where you are reasonably decoupled from your microwave circuit. For the kappa, for the Magnonic kappa that you state.
No, we discussed the way of extracting that in the paper, but we actually get the kappa, it's related to the line widths on the resonance. Okay, I would be interested if you think that this is a bad way of doing it, but the idea is that the, let's see, did I put it on here? No, I did not, but it is in the paper. So there is lots of literature on what the line width of these on-resonance things should be and the contribution of the individual elements. And we know what so what we did is we took the off-resonance resonator line width and then said the rest of the damping has to be attributed to the magnons.
So this roughly works. So my experience is that this eventually depends also on the coupling of the resonator to the environmental circuit,
Okay.
because you can de-excite via the cavity, and this looks like a loss. And if you have then more coupling, so strong coupling might be a different
Wait.
ballpark, then you see slightly enhanced line width.
I see. Would you expect the coupling Q to vary then through the resonance? Is that what you're saying?
Yes.
Okay, I don't think we saw it vary, but I can go back and talk to my student and check that. That's an interesting point. We did look at, for instance, not just the loaded Q, but the internal Q and the coupling Q as a function of field. And my memory is that the coupling Q doesn't vary. It's well captured by the fits.
Okay. So we know from independent experiments with, for example, the X-spheres, that the damping that you extract from the X-sphere really strongly depends on the separation of your microwave circuit to the sphere.
Uh-huh.
So you actually pack Teflon or whatever you find in between to get it as weakly coupled as you can get it. And only then in the spheres you will get these nice line width, and even then the Kittel mode has typically the largest line widths, or the
Yeah,
which is just due to coupling to the circuit and de-excitation via
right. But
radiation.
that part is satisfied here. The Magnon line width is much large, that we extract is much bigger than the the resonator line width, the bare resonator line width, for sure.
Okay,
Yeah.
thank you.
Yeah. I have a question. So, microphone. So if I look at your dependence, your end dependence of line width,
Yes.
so if that was, I think it's related to what that was just discussed, but if I was looking at, say, a dielectric mode in a resonator, you would get that just because there's leakage in the lower order mode. So
Yes.
wouldn't there be effect because you effectively got a evanescent field outside leaking more?
I think that's exactly what I said earlier, but in different language. So the way that I was thinking about it, or the way that I described it, is that when I think about the possibility for energy leaving the Magnon mode to leaky other electromagnetic modes, is that if I think about the uniform mode, I have this precessing magnetization, so it's projecting around this magnetic field. And then when I think about the standing wave modes, as the order goes up, more and more of that is internal. So the
Yes.
amount of field that leaves is much, much smaller.
Yes.
And so I think that explains why the line width goes down. So that's my expectation.
That's what my brain thinks.
Yeah,
too,
yeah. So then my conclusion is, so if the Magnon relaxation was a material thing that was happening inside the magnet, and it wasn't coupling to the electromagnetic circuit or some leaky mode or some box mode or something like that, then this couldn't go down anymore. It would rail at the intrinsic, whatever it is, damping rate of the magnet. Like this would start to happen, and then it would get pinned.
Yes.
But the fact that it doesn't get pinned makes me think that the material losses are quite good, and it's an electrical engineering issue that we haven't solved.
But maybe you just haven't gone up to a high enough N number, because
Correct.
there's also a frequency, they're higher frequency.
But the frequency differences are very tiny.
Mm-hmm.
So they're tens of megahertz away, sitting on top of 3.6 gigahertz. So that's not a strong dependence.
There will also be a dielectric loss, I guess, but that'll be far off.
Yeah. And by the way, I'm really delighted to hear these comments, because when we started this experiment, we were rank amateurs, and now we're just amateurs. So, all of these comments are super helpful and interesting for me.
We excited modes in a Yig sphere, quite a big one, and we polarized all the magnons away, and we were left with the dielectric properties. So that was an interesting thing to do. And we could measure the permittivity.
Greg, I have another question related, or coming back to the lower magnetization. I mean, in principle, you can compensate it by the larger volume, but that means that you have a larger mode volume, and in principle, you dilute your system. So that in the end, it means that you cannot get the same strong coupling as you can with a higher spin density, or because if you want to go to a stronger coupling, smaller volume, you have less spins.
So that's correct in every way. But the question is, what do you need your coupling for? So we easily cross the border from, like some Purcell regime or something into a strong coupling. And people are interested in ultra-strong coupling and whatever, but for most of the quantum applications, I think you actually want the right coupling, not just the biggest coupling that you can make. So the question is can you get to the coupling that you need for your thing that you're trying to do? And I think the answer is yes in this system.
There's no doubt it's a very nice experiment.
So, shall I continue? Okay, so I have now some theory that I'm going to tell you, and this is where my comfort zone starts to float away. So please bear with me. All right, so why did we start on this theory? So, there's been a lot of work on strong coupling, and as I discussed in the beginning, it's mostly what I'm going to call XX coupling that I described earlier. And so then the question is like, okay, well, what is the applications for this, and what are the bottlenecks? And there's lots of interesting theory papers out there, and lots of interesting experiments. So, like people are interested in the non-reciprocal properties of magnons. Dennis talked about, couplers to spin qubits, which is, I think, pretty interesting. And so if you can imagine, I couple my magnon to my superconducting circuit and then my magnon to my spin qubit, then maybe I have a way of, doing some interesting thing there. And of course, I'm always interested in hearing what people want to do. And I think that's really crucial to have that discussion. But the bottlenecks are super obvious, okay? The first point is the big one, in my opinion, and that is magnetic damping and line width is simply too large. It is scaring off the superconducting resonator or the superconducting circuit community. Now, there's some other ones like if you want to make microscale like circulators or circulators that are integrated with qubits, actually the insertion loss is hard in microstructures. That's why circulators are this big. Okay, if you make it big, insertion loss is great. If you make it really small, it's hard. We can have a discussion about that later. People here probably know better than me. But I want to focus on this magnetic damping thing. So I was having, one of the benefits of being at a, good university is that, people visit. And so I one day was talking in my office to Will Oliver, who came to give the seminar. And Will is a, sort of famous superconducting circuit guy. And I said, and I showed him what we were doing with VTC&E, and he said, that's really, really neat. And I said, so, at what point would this be interesting for people doing qubits? And he said, when the Magnon Q is 10 to the 6. And I'm like, that's really hard. That's not something that I think I can easily, I can't wave a wand and just do that. So after kind of scratching my head, I kind of came to some conclusions. The first one is, let's look for applications where the magnons do something useful, but, loss doesn't drive the kind of quantum function. It isn't the thing that is crucial. And so we don't have to hold the magnons up to that same level of responsibility that a superconducting resonator or a qubit structure has to have. And then the second one is, gosh, we better go back and figure out what are the ultimate limits of line width. And I don't think we know the answer to that. And there'll be, I would like to talk about that with everyone tomorrow on one of the discussions. And it's not going to be a hot topic. It's like the oldest topic in Magnonics. So sure, whatever. Okay, but let's talk about the first one. So it led us to this idea of nonlinear cavity magnonics. Of course, I'm sure many people have already thought about nonlinear before. But what we wanted to do very specifically is try to realize the optomechanical interaction Hamiltonian in cavity magnonics. Now, one of the reasons for doing this is that people in cavity and optomechanics have already thought of everything. So this Hamiltonian, once you figure out how to realize it, is got tons of applications, and then you can just go to the optomechanics literature and just cherry pick good ideas. So in optomechanics, for those of you that are unfamiliar, which I don't know, some of you I think are more expert than me, but the basic idea is that you have an optical cavity of some kind. There's many kinds. And so there's some, laser input, and then there's a cavity mode. And then one of the mirrors, for example, is coupled to a mechanical oscillator. So you have, for instance, a radiation pressure force in which the number of photons that are circulating in this cavity will then affect the displacement of this mode. And then optomechanics people are very clever, and they came up with all these modulation schemes that can lead to interesting function. So, what we're going to go after here is, so the green operators, so this is the occupation, the number of photons in the cavity, is actually going to be the magnons. And so just like in optomechanics, the optical line width is always way bigger than the mechanical line width, right? The mechanical line width is kilohertz or even megahertz, millihertz, depending on the system. It's very, very tiny. Whereas the optical cavity, the line width might be a terahertz, okay? So it's very different. They also have very different frequencies. And then so in our case, we're going to use the magnons in place of the optical cavity, and we're going to use the resonator photons of an electromagnetic cavity in place of the mechanical resonator. And what I'm going to show you is we think that with reasonable parameters, you can do things like squeeze the mode of a superconducting resonator and do cooling and lasing in that system. Okay, so here's the basic, yeah.
Can you give me a quick rundown how you implement this coupling with this structure?
I will do that, yes.
Okay.
Yeah, I'm doing that soon. Yeah. Okay, so the basic interaction I'm trying to describe here, and I haven't talked about this a lot of times, so I know I haven't perfected how to present this. But I want to draw you to the geometry of this. So we actually present two geometries. I'll talk about both, and this first one might be a little theory land, and then the second one I think is more reasonable, but it's more complicated, so I want to show the simpler one first. So, so this is a lambda over 4 superconducting resonator. On top of that, near the current antinode, there is a piece of YIG. Okay, we can also do it with VTC&E, as I'll show you in a minute, but this is the reason why I chose YIG first. And on top of that, we have a drive line. Now, experimentally, I don't think this will work, but in principle, if I orthogonalize the directions of these, they don't couple. So I could drive the YIG and then have the cavity, and not one doesn't affect the other. Okay. And so just like when you think about the radiation pressure force in optomechanics, the issue is that in the radiation pressure force, the cavity will shift its frequency when the mechanical resonator's mirror gets displaced. So that's kind of the simplest way to think about this. And so to calculate the coupling, what we have to do is think about what does a 0-point fluctuation of the resonator's flux that generates the Ørsted field around this thing do to the frequency of the magnons. Now, in an ordinary cavity Magnonics experiment, it does nothing because the magnetic field is applied along the direction of the line, so that the fluctuations will displace the magnons. But here we've changed the magnetic field 90 degrees so that this is the sort of parallel pumping kind of geometry. So the flux here does not excite the YIG in with one magnon, but or with one photon, sorry, but fluctuations of the flux through the current will shift the frequency of the magnons. And so in order to calculate the basic coupling, what you have to do is you have to figure out the frequency shift of the Cattell mode due to the 0-point fluctuation of the resonator. And so that's what I'm showing you here. And then once you figure that out, you can just pretty much look up all the equations and just derive them for the magnons that is in the same way. I said it was deadly easy. I mean, we really are just stealing whole cloth from optomechanics. And so I won't go through math because no one cares, but what I will do is tell you that the same basic formulas are there. So what you're seeing here is the change in the electromagnetic resonator damping rate, and it depends on the magnons. And likewise, the resonator frequency can depend on the magnons. Depending on the regime, you can access these different resonant conditions. So it's like left and right, sideband cooling, all those kinds of things can be done. And so, in fact, here is some plots showing that. So here is a plot of the frequency shift of the resonator and the damping rate of the resonator, its shift. And you can see even in the line width, if you just this would be like simulated network analyzer measurements. You can see that if you drive the magnons with reasonable parameters, and you please go look at the paper and decide if they're reasonable on your own. I didn't put up a table of parameters, but anyway. You can see, just by your eye, that the line width can change and the amplitude can change depending on the conditions in which you drive it. And this is all known from optomechanics. So now I want to show you how we think it's actually more reasonable to do this. Here I'm going to switch to VTC&E because it's my favorite material. We got rid of that top drive line. And what we did instead is just apply the magnetic field at 45 degrees. Okay, so now you have a component in the kind of parallel pumping geometry and a component, in the conventional geometry. And what we're going to do is take advantage of high order modes of the resonator. So this is a resonator that has, it's fundamental at 0.5 gigahertz, just like an optomechanics that's like a low frequency resonator. And then the Magnon mode is going to be at 20 gigahertz, okay? And we're going to have two close-lying harmonic modes of the resonator, one at 19.5 gigahertz and one at 20.5 gigahertz. And the advantage of this is that we're going to just drive into these higher harmonic modes, and they are going to then, which is going to be more power efficient, so we can excite the Magnon very, very efficiently by driving into these modes. They're X coupling, okay, regular coupling, and then we have the X-Z coupling primarily to this low frequency mode. So, so what I'm going to explain to you now is a protocol that we just, again, stole. You can look at these papers. But basically for squeezing the mode of the electromagnetic resonator in a CW way by just driving into these higher harmonic modes. So what this plot is I'm showing you is, here is the uniform Magnon mode resonance. Here are the two harmonic modes that we're interested in. And then here is the low frequency mode of the resonator. And, if I do nothing, then what I'm going to see is if I look at the, kind of spectroscopy of the resonator in XP space, if I think about it in terms of mechanical oscillator, but in phase and out of phase is fine if you prefer that language, then I'm going to just get the regular sort of lowest frequency mode. I cool it down. There's just, not many magnons in there, 0 magnons on average. But there is canonical commutation between X and P, and so I have this line width. Yeah.
Sorry, just a naive framing question to make sure I'm following you. So when you talk about the omega 2 and omega 3, am I to interpret those as sort of sidebands of the mixed Magnon photon excitations? So they're offset by the low frequency mode.
Yes.
From the Magnon mode?
Yes.
They're not harmonics of the cavity excitation.
No, they are both. So I'm going to have modes that sit here because I have a lambda over 4, so I'm going to get standing waves at every time I meet the boundary conditions, which I happen to do at these frequencies.
But not at 20?
Not at 20.
Okay, so that's just how it works out. Okay.
Yeah, you'll see why this matters. Okay. So, if I look at, for instance, when I drive, here's the magnetic field, here's the drive. So I actually get little avoided crossings with these mode if I just do the standard like VNA spectroscopy in my computer, or actually in Chin's computer, not my computer, but okay. So what I'm going to do now is I'm going to tune the magnetic field so the Cattell frequency is right here at 20. And then I'm going to drive simultaneously on omega 2 and omega 3. Actually, it's not exactly equal amplitude. It's close to equal, but there's papers from Osh Clerk especially, who pointed out that some differences make it more efficient, but okay. The point is, let's just imagine for the simple picture that I drive them the same. That means that, I write down my 2 cosines and I'm gonna get something right here, okay? So that's gonna efficiently drive the magnons, but it's modulated. And that modulation is going to be applying these damping and frequency effects onto the fundamental mode. And so this protocol is just adapted. So please don't think that I did a good job of thinking these things up. I didn't. I just did a mapping and then said, oh, look what can happen. The point is that once you get this modulated drive at the magnon frequency, what you're effectively doing is you're squeezing in the rotating frame of the magnons. So this thing is like going and you're squeezing it in phase with the fundamental mode of the cavity. Okay, the magnons are squeezing the resonator. The magnons don't get squeezed. The resonator gets squeezed. And so these plots indicate that. Okay, so enough said. So we did our calculations. We used reasonable numbers just to kind of put a fine point on it. We get 4 dB of squeezing below the 0-point motion of the resonator with minus 31 dB of driving power. We think this is something that you can do in a dilution refrigerator without heating it up. There's a question, maybe that's not true, but we think that if you take some care, that can be done. So we're interested in this, and we think that it can work out. Okay. So that's it. Just trying to develop some new ideas where the magnons are important and can do interesting things, but are not necessarily required to have 10 to the 6 damping before that function can be realized in practical ways. Yeah.
So you're doing a squeezing experiment with the magnons. So what can you do with that? Can you make a more sensitive output?
Sorry, the resonator gets squeezed, not the magnons.
Yeah, so that's what I mean.
Yeah.
The resonator's getting squeezed.
Yeah.
So is there any, can you apply that for some sort of readout for
Absolutely.
some measurement?
Yeah,
so
yeah,
what,
of
what
course.
do you have in mind?
That's a good question. I mean, I think in general squeezing is good for sensing, but I actually, you're the expert, not me. I should ask you that question.
That's why I'm asking you. I mean,
yeah, I should ask you that question.
Because you could be trying to measure a gravity wave or there's all these, or an axion or a...
Absolutely, but I'm a Magnon person.
Yeah, it's very, very interesting. Yeah.
Thank you. Okay, so anyway, yeah, so the theme here was try to figure out something that we can do that is really not limited by the damping, which VTC&E is great damping in Magnonics, but in superconductors maybe could be better. And maybe tomorrow we can talk about how to make it better if we could. All right, do I have time? I'm like out of time. Do you want me to finish the last part? All right. We had a lot of discussion, great discussion, but okay. Now I want to talk about one last experiment dealing away from cavity magnonics, actually back more to the theme of what Dennis discussed, where color centers are interacting with VTC&E magnons. And actually, this is about precision measurement. Okay, so it's not actually about strong coupling or anything like that. We didn't try to do that. One of the things that many of you will appreciate is that in magnetic measurement, people rarely report quantitative cone angles. They say, oh, I have an FMR line width of this, yay. They rarely report cone angles. Can they? Absolutely they can, but it's rarely done. You agree, right? Yes. Yeah, it's possible to do. Yeah, it's an extremely painful thing to do, exactly. So, it is an important thing for many applications. So when you have to do it, you can do it, but it's really hard. And, when we're thinking about like conventional measurements like FMR, regular measurements, what we're really doing is some kind of analog thing where we're doing a chain of calibration. Like we need to know, the absorption, we need to have standards and references. It's just awful. Each of those calibrations, there's like a chain of calibrations. They're each subject to error, so that the reported values are not very accurate. Often one thing that people do, which is kind of the worst thing that you could, but it's not good, is just drive it up until it's nonlinear and say, we know that it goes nonlinear at this point, so then we back off the power and we say, we know the cone angle. But that's pretty not accurate. In addition to not knowing the cone angle, we rarely know the microwave field amplitude accurately. This is something that is like metrologically very hard to figure out, okay? Because just like I have standing waves in my line and like exactly how much power I apply, who knows? Okay. So, you guys are all familiar. You can do inductively detected FMR. I picked stuff that I did in my group because they were easy to find, but we all know that everyone has done a lot of these experiments, so please don't feel offended. You can do MOC. You can do something that only my group does. You can do device measurements. So like STFMR might be one of the easiest ones because the kind of you can measure the magnetoresistance. But even there's a chain of calibrations that have to be done. All right. What we decided to do is actually start by thinking about this paper with Dennis. And he already talked about it, so I'm not going to say much about it here. And the goal of this was not, the goal of the work that I'm going to tell you about now is not to realize this proposed theory or this proposal from Dennis, but actually just use the interaction of NV centers with magnons as a way of actually getting more quantitative on measuring FMR. So let's talk about that. So how do you measure FMR with NV centers? So it's tempting to think that the only thing that one can do is just go to this resonant point, which if that were true, that would be pretty useless. Because as Dennis pointed out, like if you want to get to strong coupling, that's what you have to do. But I can do spectroscopy of my magnon right there. That's it. There's no other place where they cross. So that's a problem. But actually, now a decade ago, Chris Hamill's group at Ohio State showed that actually if you just have NV centers and you stick it on YIG and you blast it with microwaves, you start to see the FMR lines of the YIG. And originally they were very puzzled as to why this was going on, but it was eventually sorted out. And it's this relaxometry idea. This was really kind of nailed by Amir Yacobi's group, I would say. But also Chris's group did a lot of nice work on it. What happens is that as you drive the system really hard, you get multi-magnon scattering, and that raises the frequency of whatever your lower frequency magnon modes are to the frequency of the NV center spin transition as incoherent noise. And that suppresses the T1, which just in a continuous wave measurement turns out to just give you a contrast. And so that's what's happening in these kinds of measurements. And this has all been really beautifully mapped out. So you can do relaxometry, but this does not tell you anything quantitative. Actually, no, it does. Actually, Chufeng Du has done a beautiful job of doing things like figuring out spin diffusion properties, and there's actually a lot of beautiful work on relaxometry. But it doesn't help with the quantitative measurement problem. Okay. So what we're going to do is do a different, very, very deadly simple approach. I like simple approaches. So the simple idea is that if I have some magnetic precession, then the average moment along the z-axis, the static magnetization, starts getting smaller, okay? And if I have an NV center sitting in the dipole field of that thing, then it's going to notice a change in the average field. So because NV centers are just like massively excellent magnetometers, I can just use that sensitivity as a way of measuring out this change and then back it out to the cone angle, okay? So here is the structure that we use for that. This is actually a pair of VTC&E disks. The main reason for the pair is that you get a more uniform field, dipole field in between the disks than if you just have one. Now the NV centers, it's not a single NV center, it's actually a ensemble measurement with a whole plane of NV centers that are implanted 50 nanometers below the surface. We apply the total magnetic field, including the dipolar field, to be along the NV center's symmetry axis, just to make the measurement easier. We have this loop antenna to excite the disks and the NV center. We can just put, it's kind of like, it's not resonant, so you can put any color in, any frequency in you want. And all these measurements are done at 200 Kelvin, which just protects the VTC&E in case we, apply too much optical or microwave power accidentally. So that's just a protective measure. It could be fine at room temperature, but you can kill the VTC&E if you blast it with something. Okay. So again, I want to be clear, like this is only going to work with microstructures. It won't work with continuous films. But if you have a microstructure, then you're going to have a dipole field. And so the total field seen by the NV center is going to be just the vector sum of the dipole field and the external static field. And we're going to apply that mostly along the direction of the NV center axis. So that's the basic idea. All right, so the sequence that we're going to use to do this measurement, we call the FMR echo sequence. It's just a very simple riff on a conventional spin echo. I think many of you know about spin echoes, but I will walk you through anyway. So what we do is we initialize the NV center into the 0 state, so just by optically polarizing it. And then we apply a pi/2 magnetic field to the NV centers. This is a global pulse, so all the NV centers this is happening together. Now, if the NV center, if the frequency of the drive for the magnons is not on resonance, or if we don't drive, actually, it doesn't make one difference or the other. In other words, if nothing is changing with the magnons, then what happens is a regular echo. So we get dephasing both from the inhomogeneity of the field within our collection, as well as from noise fluctuations. But we apply a pi pulse to refocus it. It rephases, and then I want to point out that we do a 90-degree phase shift on the final pulse. So this is along the x-axis. X is in phase or whatever. Then the pi pulse is also in phase. And then the last pulse, which is normally in an echo designed to project this coherence onto the z-axis for readout, we're going to actually apply that instead of on x on y. Okay, so if everything works perfectly, it actually stays on the equator of the block sphere. Okay, and then we'll read out an average between 0 and -1. Yeah.
So the first line is when the frequency of the drive does not match the frequency of the magnons.
That's right.
But what about the thermal magnons?
Yeah, they're there.
But are they not dephasing the spin?
Yeah, but we're refocusing them. So if you have interactions that are faster than this, then they will cause dephasing.
And I think I remember like some calculations showing that the number of driven magnons is minor compared to the number of thermal magnons. And as a consequence, the claim is that thermal magnons are gonna be dominating. For instance, the dephasing and relaxation of the spin centers. So is this in agreement with?
So we didn't do an extensive study of that because other groups have done extensive studies of that. It isn't the purpose of what we're trying to do. What we really need to do is be able to measure with enough coherence that we can, build up good signal to noise on the final readout. we're rejecting the thermal magnons in this echo. That's the basic point. Okay, so then on the other hand, if this FMR drive, which is a different frequency than the pi pulses for the NV centers, I make sure I make that point. So when I drive the pi pulses for the NV center, that's way detuned from the magnons. It doesn't do anything significant to the magnons. But when I drive on the FMR frequency of the magnons, first of all, I only do it for one of the free precession cycles, not both. So what that means is that in the first interval of free precession, not only does dephasing happen, but there's also a z-axis field in the block in the rotating frame. And so I get precession on the block sphere, okay? Then I do my pi pulse, I rephase, okay? But I don't lose the additional phase that I picked up from this changing magnetic field due to the dipole field changing. And then this angle on the XY plane of the Bloch sphere is then mapped by this pi over 2 on Y. Okay? So if no consistent drift is happening, then I still stay, at Z equals a half. But if I get a consistent phase due to this FMR pulse, then I'll see it in my Z readout of the spins. Okay? So here's an example of a typical measurement of this sample. So this is the probability of finding the NV center in the 0 state, so from 0 to 1. And what I mostly find is that I'm at a half, because that's what I am when I'm in the equator of the Bloch sphere. However, when I change the FMR drive frequency to the resonance condition, then I see that it starts to shift. Okay, and that's just reflecting the extra phase accumulation. Okay, so this is nice because I actually am measuring the phase accumulation, which I can directly track back to a change in the dipole field quantitatively. So for instance, I can do this. I'm not tethered to a particular magnetic field because I have two separate pulses now, one for the NV center spins and one for the magnons, and as long as they're not sitting on top of each other, everything is okay. So I can do this. So for instance, here is a bunch of different resonances that we did. Here's a fit to the Cattell frequency. It gives literature values. Everything looks really good. We looked at now, the main point here is the power dependence to look at how the precession angle changes. And what do you need to do? You need to essentially know how strong the dipolar field is, which you can measure with the NV centers, okay? You need to know how much it changes, which you can measure from the NV centers. That's this formula here. And then you just get your magnetic precession cone angle. And so, this is the values that we got. This red point is actually, there's a 90-degree phase wrapping. So we can't really determine if, there's a way to do it, but we just didn't think of doing it until later. And then Brendan McCulley, and the postdoc who did this work, is now at NIST and wasn't here to do it. So, okay, we didn't do it. But we marked this one in red because the phase accumulation is more than 90 degrees. So that means that there's a degeneracy in what the Z projection is. So it could be that we already hit like the Schul instability in there, or it could be not. But what you can see is for sure we know that we're getting a cone angle of a little bit over 6 degrees. And I want you to notice that also the horizontal axis is calibrated. We know the strength of the magnetic driving field on the system because we can calibrate it with the NV centers, because we just measure the Rabi oscillations at these frequencies, and then we know what the driving field is. So that evades the problem with the standing waves that you have in your microwave line that is a bugaboo for getting really well-calibrated FMR measurements. Okay. So this is my last part. Thank you very much for sticking with me, and I really appreciate all the great comments and suggestions. But this is a little thing that we did, and the main point here is that it's both sensitive and quantitative. It's not limited by specific frequencies. We think that this could now be very interesting to apply to scanning NV center microscopy, which we also do in my group. So it should be a lot of fun. So that's it. Thanks.
Thanks, Greg, for a stimulating talk. I guess we take some questions.
I like it. I have one question. So all these friendly frequencies, Rabi and whatever, this depends on the spin state that you're assuming.
Sorry.
So if it's an S equal 1, then the rotation frequency might be faster. The Rabi rotation frequencies might be faster than if you assume S equals 1/2. Because
yeah, of course.
Yeah.
Yeah, you have to know your spin that you're using. So
That's
you
what
could
I'm
do it with a
saying.
spin 1/2, but you have a different spin operator.
Correct. So now comes my question. So this shouldn't matter for the magnetic system at the end of the day, or not? Should it or not?
No. So the beautiful thing here is that what we're measuring, there might be some practical aspects, okay? But first of all, the frequency of the magnon doesn't matter. As long as the dipole field changes enough to measure, you could do it, you could drive it at a terahertz. If the dipole field shifts, that's what we measure, we can measure that, okay? So that's the first thing. The second thing is that there's that what we're really doing, and this is the sort of metrological aspect of it, is that unlike calibrating a chain of analog things, we're comparing something to a frequency shift. That's basically what this measurement does. So as a result, we have nice time standards. So it's nice and quantitative in that way.
Super cool.
Thanks.
Okay. Oh.
I have a question regarding the calculation of the angle. I was wondering if you have dipole-dipole interaction, like in your magnons, shouldn't the precession be elliptical instead of like circular? And if that's the case, how can you like take that into account?
Yeah, so that's a great question. So first of all, to a very good approximation, VTC&E is circular because we're applying magnetic fields that are far exceeding ms, far bigger than 4 pi ms. So no anisotropy in the problem is even close to the applied field, so it's pretty much just circular precession. Having said that, what we're really measuring is the change in the dipolar field. So you can find you'll have to know something about the anisotropy. You have to make some assumptions about the kind of precession that you're getting. If you know that, then this works fine. You're measuring the DC component, right?
DC, okay. The DC component.
Yes.
Or the average part for the duration of the RF.
Yeah, because if I have elliptical precession, then presumably there's like a 2 omega, but we don't see that in this.
Very interesting protocol, Greg. And so this pi over 2x, pi over 2y with the pi pulse in the middle reminded me of some like modified dynamical decoupling. So, and I'm just like wondering whether you guys have thought about including like more pi pulses in between the initialization and the readout, and how this would like help you guys if it would at all.
No, that's an interesting question. So we didn't want to make it too complicated. So this is the simplest protocol that we could do that both dealt with the inhomogeneities and, so what you would be doing if you do like, XY decoupling or CPMG or some kind of thing like that, you could protect yourself against different noise. You would still have to essentially interleave FMR in a way that respects the way the sequence is decoupling you, because basically the decoupling is decoupling you from everything, including the FMR, unless you put it in the right free evolution windows. And then which sequence, which intervals you put it in, you have to be careful that you're not suppressing the phase that you're trying to accumulate. But within those constraints, it would be fine to go to higher order decoupling.
It would not benefit.
I don't know about that. It depends on the regime you're in. I mean, it depends on how coherent your NV centers are, how close they are to your microstructure. One of the things here is that you could very easily optimize and get in a regime where the NV centers are not that close. So they're not getting thermal magnon coupling strong at all. Okay, so their T1 could be very long, and you could measure even more precisely by doing this kind of decoupling. So there could be a benefit, but you have to kind of go through a checklist, and if all those things are satisfied, then it could be beneficial.
I have another question. So if I understood correctly, by doing this kind of measurement, you can infer the value of the driving field, right?
The driving field itself, you can just measure directly with Rabi oscillation. So what you do is, I change the magnetic field. And by the way, I can just go back to the picture. All right. So I know exactly the profile of my electromagnetic field in this antenna, okay? But also I can change the magnetic field. So if I want to drive a magnon at 5 gigahertz or whatever, then I shift the magnetic field so that rather than the magnons being on resonance, the NV is on resonance. And then I just measure Rabi oscillations of the NV centers. Magnons are not excited, and that tells me the strength of the driving field. That's all we do. But I can also just measure it like over here, because I know how the B1 field varies with position. You can either directly measure it, or you can do it in COMSOL, or you can do both, and they agree perfectly. Like that part's fine.
If you had no information about the amplitude of the driving field whatsoever, but you could still measure the shift in the MZ component, could you back engineer and infer the amplitude of the driving field by just looking at the shift and the MZ and also the angle?
No, because of the line width of the magnet. So imagine that, so for instance, the damping, if you just like run a macro spin LLG calculation, you'll see that if I just set alpha to different values, I'll end up with different cone angles, okay? If I have a multimodal magnet where I have, closely spaced modes or whatever, then I'm gonna have this set of spins excited and this set of spins excited a little differently. And so measuring in one location the overall Z shift isn't enough to tell me the driving field, because it depends on how the magnet is coupled to the microwave field. So I really need to measure both the microwave field. If I want to make a plot like field angle versus driving field, I really need to measure them separately.
So, yes, it's on.
On this, if I reinterpret what you said, so you know that if you drive your magnet, you change the magnetic field, or you change the vector length of M for a known amount of time, because that's your pulse length. And this change in effective magnetic field at the location of the NV, this is what you can measure as a phase rotation angle
Yes.
in a Hahn echo sequence.
Yes.
So what you actually measure is a vector length change in M. If you know from broadband spectroscopy your magnetization parameters, which you can measure independently,
Yes.
I think then you're also there.
Yes. Yes.
You don't need the driving amplitude.
I
for
think
this.
that if you have solid if you have other information from separate measurements, then you can also arrive at similar conclusions. I don't think that you can arrive at them with the same level of accuracy. I think that I can measure the driving field far more accurately by Rabi oscillations than I can by backing out from the cone angle and the known line width.
So I have a question. The weakness of using is cos squared. The cos of theta isn't
Yeah,
data
there's a
around theta.
wrapping point, yeah.
Oh no. With measuring the cone angle by seeing how much the thing shortens, doesn't give you much sensitivity when it's very small.
That's correct. It's a theta squared kind of a thing, yeah.
And so and so you have to drive your spins pretty hard, right? So how I'm thinking about my erbium and my gadolinium vanadate, and maybe using the erbiums to measure the gadolinium vanadate cone angle, right? Do you think so? How well could you use this at low temperatures and low powers to measure cone angles?
So so there is a very deep, and so the nice thing about, so you're right, it's quadratic, which means basically in the first order Taylor expansion. However, the NV center is an excellent magnetometer. So these are pretty garbage NV centers. Like implanting and making implanted NV centers is not the best way to do things, but it is easy, so that's why we chose it. But if you have good diamond, say delta doped NV centers that are, highly coherent, reasonable numbers for a single NV center, like what we can do in scanning probe, we can measure a couple hundred nanotesla per root hertz. So then that gives you a sense of how small the cone angle can be. And actually the geometry matters. So where the NV center is relative to the dipole field, all of that stuff matters. But the good news is that you can measure it all, right? And then the question is, if you want to measure some cone angle of microradians, then you have to sit down and work through the math of, what's the best way to do that. So ultimately, you're right, you're going to run out of signal.
I was just wondering whether you guys have thought about doing temperature-dependent measurements and verifying the Bloch law, the temperature dependence of the Bloch law of the magnetization of VTCNE and other materials.
That's a great idea. Thanks.
I would have a question to the second part of the talk, to the optomechanics with magnons. So
yep. Let me just find it again. Which part do you want?
I actually would like to basically know roughly G naught that you can achieve.
G naught?
G naught, the single photon optomechanical coupling strength, which you would estimate for this structure.
It's right there. It's 12 hertz.
Oh, that's not so bad. Thanks. I missed this number, sorry.
And that's sort of the same as the G for XX, right? It's just usually...
No. G for XX is, so these have a different relationship with the volume scaling. So, the strong coupling experiments, G for XX was 90 megahertz, not 12 hertz. Oh, you were saying per spin?
Yeah.
Actually, they are close to the same, yeah. I think our per spin it's of the same order, yeah. That's right. in the lumped element devices, it's like 6 hertz or 8 hertz, or I forgot what it is. I don't know.
But this only works collective, isn't it?
Yes, that's right.
Okay.
Sorry, this is exactly this. So there isn't a root end thing. We talk about this a little bit in the SI, but because a reviewer asked about it. And the key thing is that if you make this too small, actually the problem that you run into is you can't increase the number of the total magnon number becomes a problem. So you saturate the system before you can, because like in optomechanics they talk about the total optomechanical coupling, which is like big G, which is the number of photons in the cavity, or root n photons in the cavity, times the bare coupling, which is what this is.
Mm-hmm.
And then you get to numbers that look like megahertz because the cavity occupation is high. And that's the situation here. So this is the little g, okay? But the big G is also limited by the number of spins, not in the same way. It's limited by, essentially, if you have a very tiny element, then you can't increase the number of magnons because you can't make more magnons than spins. So if you, right, that's it. And then there's also some geometrical considerations with the resonator itself.
Okay. You could do this, or you could boost this number quite significantly by not using an inductive coupling scheme, but just put it in a squid, in a flux tunable resonator.
Yes.
So
that's a very cool idea. Yes, I agree. But baby steps.
I can tell you the flux tunable resonator in the magnetic field is a painful undertaking.
All right. We've had a lot of questions. I think, do you want to?
Yeah. Thank you, Greg, and thank you, Yvonne, for sharing kindly. So, two things. So tomorrow we're going to have our dinner. So I strongly recommend you not to go to a place called Picanha na Tábua, because that's where we're going. And we also have a group picture for the second week. So wear your Sunday best, comb your hair if you have any. So so that's it for today then. So see you tomorrow at the same time. Have a nice evening. Thank you.